about specific paths through your code and the sequence of events that takes place. And it's giving you some diagnostics of the decisions it made and what it saw. So in this case, on line 9, we see that there's this if statement where P is tested against null. And at this point, the analyzer is assuming, well, since I'm not going to necessarily make any assumptions about P before it came in, but since you're actually testing it against null here, I'm going to assume that it could be null. And so then on the false branch, P is equal to null, and then it's dereferenced down below. Now with the power of the source location information we have in Clang, we can get very precise information about where the actual expression was and so forth. Now, I want you to pay attention. See, null is in red here. Null is actually a macro. And the really cool thing about integrating the preprocessor directly into Clang is that we can actually expand the macro definition right there, showing you exactly what the compiler saw. And this is a really simple macro, but these can get very complicated, and a lot of logic can be embedded in macros, and a lot of bugs come from this. So this is a really powerful kind of way to view your results. We're also not easily fooled by just simple castings. Here you're actually assigning the value of a pointer to a uint pointer t, so it's just the integer representation of the pointer. Then you actually test the value of that there, and then you assign it back to another pointer, and then you can actually see that there's a null reference there. So there's actually some fairly sophisticated value flow. And then here's just another one I think is very cute, returning an address of a stack variable. As you see right here, we actually say which variable it was that was returned. We assigned its address to y on line 5, and that's where we return it on line 7. We actually track which variable it was. So there's a fair amount of sophisticated reasoning there. And these kinds of diagnostics can be very effective at just telling you exactly what's wrong. So that's great. So how does that actually work? And again, the next few slides are going to be fairly pedagogical, just kind of giving you a flavor of what are the trade-offs in different kinds of analyses that we can implement in order to find bugs. So we can, from what we've seen from a lot of different tools like find bugs, Covarities Prevent, and so forth, there's a lot of different ways to find bugs with different degrees of analysis sophistication. And some bugs just happen on individual statements. You can find some of those bugs very accurately. I showed that with the printf example. Some bugs require analyzing the scope of an entire function, like the ones I just saw. And others involve really doing some kind of deep analysis across the whole code base, looking how one function calls another, which calls another, and so forth. All these are important, and all of these require different levels of analysis time. And so some of them fall very naturally into different workflows, doing regular checking every time you build, or perhaps just as a nightly regression. Now I'm going to show you a trivial example of a check that we can do at compile time. It's a valid warning, and then show how it easily breaks, and give you an idea of when we have to actually crank up the analysis power. So this is a simple example where we have x declared at the top, and if y is 0, we actually don't assign it a value, and then we return it down below. Both GCC and Clang, as part of their standard compiler warnings, can emit a warning for this. Clang actually shows you the use of the variable. So this is actually an accurate error. And so what's going on here? So this is a source level control flow graph. We have these in the LLVM IR. Same analogy can apply to C. In Clang, we also have source level CFGs, which look essentially like this. And so what happens here is that both the compiler analysis sees this edge between the top block and the bottom. This is the path that I'm going to assume through the code, and x is not assigned a value at the top, and it's used at the bottom. So this is the path that it believes existed. Now, if I modify the code just slightly and add a guard on the actual use of x, it's almost exactly the same. The control flow graph just changes a little bit. But what's interesting now is if I run both Clang and GCC on it, they emit a warning, even though this is completely bogus at this point. And so this is one reason why people often just ignore these warnings, because at this point it becomes useless. It's just noise. So what is going on here? Well, essentially there's two feasible paths through this CFG. The first case is that both branches are taken, right, because they're control dependent. You know, if y is 0 at the top, it's 0 at the bottom. In the other case, that y is not equal to 0. It could be any value not equal to 0, which is fine. In that case, both branches are taken. Actually, both branches are taken. Now, the problem is that the analysis being done by GCC and Clang, when they're just doing these very simple warnings, thinks that there's this path through this code. So it's just like magically the value of y suddenly, you know, this is what from the programmer's perspective just changed, that the analysis isn't picking this up. And these kinds of false errors can happen very much in practice. And it's basically because they're not tracking the information from these branches. So we have a name for these things, and they're called false positives. They can occur for a lot of reasons. The one I just showed you is false paths, so just a path through your code that's just not feasible. And the other thing is that the compiler or analyzer or whatever you want to call it just has insufficient knowledge about what your program does, how it's being called from the outside world or whatever. And some of this information can be repaired by you telling it more stuff, but at the end of the day, it can only operate on the assumptions that it makes. And if it makes a false assumption, it can spit out noise. If you contrast this with testing, when you're testing code, you're actually really running it, right? So if you've recreated all the situations which the code would run in practice, a bug found by testing is a real error. So we got a lot of ways to reduce false positives. The biggest way is to just crank up the analysis, and I'm going to talk about the implications of that, and that's actually gone into what we've built. But it's just difficult to eliminate them completely. So what do normal compilers do? There's actually a name for this, and this might be pedagogical. I'm not certain how many of you know this, but essentially it's called flow-sensitive analysis. It's where the compiler can reason about the flow of values through the program as they're being executed, but it doesn't keep track of information from paths. So if you think about these guards here, you know, it doesn't know about, when it gets to the ++ x, it doesn't actually have any information about what x is. LLVM's SSA form with its phi nodes and so forth is designed essentially for doing efficient flow-sensitive analysis. And what happens with a phi node is that at the end of this branch, you're going to actually merge information here, right? That's how you don't get an explosion of information. The great thing about these is that they're fast algorithms. They can be used by optimization and compiler warnings. And this is really